So I'm very pleased to have Kasja Rejzner for her second lecture.
Right, so welcome back, and I appreciate you woke up early in the morning to come here. So let me review quickly where we finished the last lecture. So I talked about constructing models in perturbative algebraic quantum field theory. So I introduced some classes of functionals on the space of field configurations. So I talked about local functionals, I talked about multi-local functionals, okay, and I also talked about regular functionals. And the regular ones were somehow the nicest in the sense that all their derivatives are smooth. Then I introduced some products. So I introduced the star product. Actually, no, first I introduced the pointwise product. Okay, then I introduced the star product, which was defined using something which corresponds to the two-point function. So that was the proportional, the antisymmetric part is proportional to the difference between retarded and advanced propagators, and there is some symmetric piece. And then there was the time-ordered product, which was defined using the Feynman propagator. Dramatic music. So the main difference here between these two objects, well, obviously you can see that there is a plus here and the minus here, and what it does is that here the singularities at zero cancel, so this is pretty harmless, so that is defined, for example, on this space of multi-local functionals, but this is not. So I singled it out as a problem, and this problem I'm trying to address today. Okay, so good things. So what do we know about it? So I said, yes, it's defined on regular functionals. These are not enough. But it turns out that it's also defined on local functionals as long as we are looking at things with disjoint supports. And why? Because the ugly singularity here is on the diagonal. So I also gave this relation that F time ordered G is equal to F star G if the support of F is not earlier than the support of G, and the other way around. Okay, and looking at this, you can immediately see that, of course, if we have things with disjoint supports, then, okay, well, maybe it's not clear necessarily, but if we have things with disjoint supports that we can also split into smaller pieces, such that these smaller pieces can be ordered in some way, then we can actually write time-ordered product with respect to the star product. Sorry, write time-ordered product using the star product. And star product is well defined. So the only actual problem is if these supports would overlap. Okay, so here is a fact, which is, well, the consequence of this relation. Okay, and you can also check this if you want to do some microlocal analysis in the afternoon. So let's take the n-fold time-ordered product. Okay, so this is Tn evaluated at a bunch of local functionals. Okay, this is defined, okay, as you think it is, right? So it's F1 T Fn. So this n-fold time-ordered product is well defined as long as all these guys have disjoint supports, pairwise disjoint support. So no overlaps whatsoever. Is well defined if F1 to Fn are local with disjoint supports. Okay? So we have it on some functionals. Now, this is clearly not enough, because what I want to do is to use this to construct, say, the S matrix. So we actually need it for overlapping supports. So let's recall another fact from last lecture. So the S matrix, or local S matrix, is S of V. I said it was time-ordered exponential. Okay, now with this notation of these Tn's, can actually write it as follows: n equals 0 to infinity. Let's see, so we want I over h bar to the n, 1 over n factorial. This is an exponential, so it does these things. And then Tn evaluated on V tensor n. Okay. You see, this actually has negative powers of h bar, so maybe, just to be on the safe side, I should introduce another formal parameter. So I told you that h bar was a formal parameter. So actually, to make things precise, I'm going to introduce the coupling constant into this. Okay, so lambda is another formal parameter. So this corresponds to the coupling constant. Okay, so here the problem we are solving, we are working with things which are formal power series in lambda, and they can have negative powers in h bar, at least this object does. So we want a Laurent series in h bar. So I guess we want f, so goal is to define things on f formal in h bar, and these are coefficients to Laurent in, formal in lambda, and Laurent in h bar. So if people don't know what that is, it actually just means that, you know, it's not a formal power series, because it can have negative powers of h bar, but only finitely many. Okay, so you never have a situation where you have an infinite series sort of into the negative powers of h bar. Okay, but that's still, even with these caveats, right, formal power series, formal parameters, I'm still not done, right, because here, this is an actual problem. So if V is local, so let's write this here, if V is local, then obviously this Tn, right, I cannot use this fact that it's well defined for disjoint supports, because, well, V obviously doesn't have a disjoint support with itself. So we have to, for the actual application I have to solve that problem. So now I'm going to solve that problem. So this is a bit of technology called Epstein-Glaser renormalization. It was slightly underappreciated in theoretical physics because, when you see it for the first time, you wonder, why do you bother? Because it doesn't really tell you how to compute things more efficiently with respect to the, traditional approaches to renormalization, say Wilsonian. And it works with, fairly advanced mathematical objects. So why do it? Now, for me, the answer why do it is that I'm really interested in these algebraic structures. I want to be able to define these products. And in the end, I want to build the BV algebra or the family of BV algebras for various regions of spacetime. So I really need to understand if this algebraic structure of the time-ordered product can be extended. So, from a practical viewpoint, if you want to be able to prove theorems and have sort of structural results, this is actually a good way of thinking about it. So it works by giving a set of axioms, or in other words, a wish list for what these Tn's are supposed to be. So there are axioms for these Tn's. Okay, so the first one, maybe it's a bit silly, it's just, okay, so what's T1? We have to fix T1. So the time-ordered product with one argument. And let's say it's actually not a bad idea to set this to be identity. Okay, one can do something more general. So you would do something more general if you want to have a flexibility to change normal ordering. If you change normal ordering. Okay, so that fixes the starting element. I want some sort of symmetry. Okay, so this is supposed to be a commutative product at the end of the day. So Tn is, well, I want to say symmetric, but watch out, we were working with graded objects, and there's going to be more graded objects later on. So there were those anti-fields which were commuting. These are actually not really affected by the time-ordered product, but for the future, when I'm going to talk about gauge symmetries, and we'll introduce those ghosts and anti-ghosts and other things that Pavel talked about, these are graded. So what I want is graded symmetric in its arguments. Okay, so these are actually pretty obvious in the sense that, well, they don't say anything really deep about the product. So here comes one which is actually crucial and somewhat defining property for these guys. So this is called causal factorization. So causal factorization property. Okay, and it looks like follows. So let's say we have a bunch of these F1 to Fn, which are not all pairwise disjoint, but I can split them into two groups. So I want to look at this, where I have a bunch of those guys, say like that. Okay, so this is F1, F2, and Fk, and I have another bunch, say here, and this is Fk plus 1, and so on until Fn. So I can split them into these two groups, and so the precise way of stating this, okay, so here I said slightly informally that f is not earlier than g. What does it actually mean precisely? It means that f does not intersect the path of g. So this is j minus of support g. And here the same. I want these guys not to intersect the path of these. So this would be, yeah, so you can see that they're in the future or space-like. So in the future or elsewhere. Another way of finding out if I have this configuration, well, I can draw a Cauchy surface that separates them. So separated by a Cauchy surface. Okay, so if I have such a configuration, then this product actually is supposed to factorize. So this is this property I'm asking for. So I want to replace the product between this bunch and that bunch with the star. So these guys come first. So I have here tk of f1 to fk, okay? Then I have a star, right? And here I have tn minus k and the rest of these guys. So fk plus 1, f to, let's see, so 1, 2k, fn. And, well, this is the special case of that with just two arguments. What do we see here? Well, first of all, I'm trying to trade this time-ordered product for the star product, right? Because I know it's well-defined. And second of all, you see that, well, naturally, this k here has to be less than n. Okay, so if I had the prescription for tn's, or well, tk's for k strictly less than n, then I can use that to construct more general tn's. So it's almost what we want. It's going to be one more property. So another one which is actually useful here, I want these tn's to be in some sense differential operators on the configuration space with coefficients that don't depend on fields. So I want, this is maybe a slightly informal way of stating it. I don't want to write long formulas. So if I take a functional derivative of Tn of f1 to fk, I want this to actually just act on these functionals. So this is supposed to be some k equals, sorry, I equals 1 to k d f1 over d, oops, differently, Tn, and here d f1 over d, no, yet another way, sorry. Let's do it like this, d fi over d phi of x, and here f k. Okay, so that's kind of commuting with the differentiation. So this will be useful in well, determining these time-ordered products, not in terms of complicated functionals of phi. This actually guarantees that Tn's have to be differential operators with coefficients that don't depend on phi. Okay, so they are just some distributions. So this tells us that Tn does not, or maybe are differential operators on the configuration space with distributional coefficients independent of phi. Okay, one more just for the road. Yes? Signs? No way. Yes, there are signs. There are signs. Okay, so this is here with signs as appropriate. So if these are all bosonic, this is how it looks like. Sorry? Yes? Sorry, they're what? That's correct. For actually space-like separated functionals, let's see. So we can make an experiment, right? So I don't have this on the board anymore, but there is, so in that formula, there were two pieces. One was antisymmetric and the other was symmetric. Symmetric was H. So let's think about the antisymmetric piece, which was built from retarded and advanced green functions. So what does it mean? So retarded green function has support to the future, advanced to the past, right? And then, so if you just look at that piece, and then you compute the star product with just the antisymmetric part of two space-like things, it's zero, right? Because it only can have, so you take the support of the first guy, then you propagate it with these green functions. It can only go to future to past, and then it doesn't overlap with the other guy, right? So the antisymmetric part would give you zero. The symmetric part could give you something non-trivial, but then it's commutative, right? The symmetric part gives you commutative product. So yes, you have commutation at space-like separation, which is actually, if you go back to my first lecture and the sort of first, introduction into this formalism, you want things to commute as space-like distance. This is the causality. So this is actually a very good point. The fact that this is called causal factorization is not a coincidence. So this actually guarantees that what I'm going to build in the end satisfies causality in the sense of AQFT and Hack-Kassler axioms. So thank you for the question. Any more questions at this point? Okay, so let me state another axiom. And this one I'm going to state in terms of S matrices because it can be stated with respect to time-ordered products, but it's a total mess. So 5, it's unitarity. So it essentially says that S has to be unitary. So S of V star S of V complex conjugate, or maybe actually let me write it this way. This is complex conjugate equals 1. So this is complex conjugate. Okay, but you can sort of expand this condition in terms of these time-ordered products using the formula or the Taylor expansion. So it actually can be written in terms of time-ordered products, but it's a mess. Okay, so these are the axioms. You can throw in some more. So sometimes people do throw in some more because on curved spacetime you might want to have stronger properties, so some sort of analyticity of these coefficients here and so on. But let's not do that, okay? Let's not do that. Let's just focus on the sort of basic setup. So now, after listing this, you can probably almost see what I'm going to do. So I said that this property here is telling us how to construct Tn from lower order TKs. And this is exactly how the proof goes. So Epstein and Glaser have shown that there exists a family of Tn's satisfying these properties. So just state the theorem. Okay, so there exists family of Tn's and in N satisfying one to four. Okay, proof. I'm not going to prove it because this is not a lecture in Epstein-Glaser renormalization. But if people want to look it up, I'm happy to discuss it with you. But here is the idea of the proof, right? So so this is by induction, okay? So by induction, so show that given Tk, k less than n, I can construct Tn. Okay, and how do I do that? As I said, I take these arguments here. If they have some sort of weird overlapping configurations, I'm going to use partition of unity to split these local functionals to smaller pieces. And then I'm going to use this property, okay? And the only points where I cannot use that to define Tn's are the overlaps of supports. So this is essentially the idea. Maybe instead of doing the proof, I'm going to do an example which kind of connects to Feynman diagrams, more traditional QFT, so that you can see what's going on. So this is the sort of general setup, and now let's do an example. This is not something that Epstein and Glaser would ever have done. They were not into examples, but hey, okay, it's been a while, right? So one observation I want to make is that Tn can actually be written in this form, Fn. Actually, no, sorry. Let me do it. Let me do it in the sort of more straightforward way. So we started, well, last lecture, I told you that there is this time ordering operator that allows us to write T in a nice way. And this was h bar half Feynman propagator d squared over d phi squared. Okay. I want to write it in pictures. So here is a picture. I can represent the Feynman propagator as an edge, GF, and I want to, well, actually, sorry, that's not the best way of doing it, sorry. Let's see. Let me write this like that. H bar. Okay. Okay, sorry about that. And yeah, just to, there's not enough letters in the alphabet, and F and G are so good. So I'm going to do F1 and F2, which is hopefully not too confusing. Okay, so I'm doing this one, and this I'm going to represent as an edge, okay? And here the derivatives are attached at the ends, and these are sort of like empty circles, d over d phi of y. What's in the middle is gf of xy, okay? So that's how I represent this operator, this bidifferential operator. And then F1 and F2 are local functionals. If you have done some quantum field theory, then you might have seen the Feynman graph notation. So I'm going to represent those as vertices. So these are going to be local vertices, okay? So the number of legs corresponds to the degree of a polynomial. So this, for example, if I put here a test function and here another test function, so F1 here would be phi cubed with F, and then phi 2 would be phi to the fourth with G, okay? So because these are local functionals, right, I can represent them as a vertex with legs. And now if I want something more complicated, so if I want, say, derivatives, I can add some decoration. And of course, here, the way I wrote it, it seems that I have just one field, but I can add any decoration I want to these edges to have different kind of fields. So plus decoration on edges and vertices. Okay, so this I hope makes some connection to what people know. And now when I apply this operator to these functionals, what do? I'm going to pair those loose edges with those circles. So a derivative like that eats a phi, right? So this circle sort of cuts one of these external legs. This is very violent, and then you create a line. So for example, that's a cute combinatorics. I really think that there's something very useful with representing things visually. I'm a visual person, so that's why I like it. But yeah, let's look at an example. So we have this guy, and I'm going to write it already like this, applied to phi to the 4 theory, so to things like that. And, there's going to be a lot of graphs that contribute, but I'm going to just focus on one where I take two edges of this, contracted with two legs, and one of the things I get, so I'm going to engage two on one end and two at the other end, and this is the fish diagram, okay? So there's going to be a lot more. If you want, you can try to, actually work it out on your own. The fact that you have the exponential actually takes care of the combinatorial factors that you would normally put on Feynman amplitudes. So here I have the following: G f of x, y, and then G f of xy. So you can think of these Tn's that I told you about as expanded into these Feynman graphs. So now the problem that I singled, that these time-ordered products are not well defined for coinciding supports, this corresponds to exactly the divergence of this graph. By the way, I'm working in position space. If you're not used to position space, then this might come as a shock. So in momentum space, you would write everything in terms of momenta, and then you have convolution of things, and there's a momentum integral over a loop. Now take the Fourier transform in your head. This is in position space. So what is convolution in momentum space is just multiplication in position space. So what do we have here? So with that diagram, the problem is gf of xy squared is a horrible idea. So this is not a well-defined distribution, but okay, we can actually cheat slightly. We can define it as a distribution on m squared, that would be bad, but minus the diagonal, okay? Diagonal, and this is the set of points x equals y, okay? Diagonal. This is fine, okay? This is fine. So I can understand this as a distribution on m squared minus the diagonal. So in other words, coming back to this general story, as long as the supports are disjoint, I'm fine. So now my mathematical problem is, how do I extend this, okay, to a distribution that is defined on m squared, okay? So that's the induction step of Epstein-Glaser, is to be able to construct those extensions. They were not very constructive people, so they actually showed existence. Nowadays, we do a bit more computation, so you probably want to get a number. Okay, so how to construct this extension? This is related to another piece of mathematics, and again, this is not a course of microlocal analysis, so I'm not going to give you details, but I'm going to give you a reference. So to extend distributions, okay, look at, there's a beautiful book in 4 volumes by Hermander. Okay, now I always forget what's the actual title. But anybody in the audience? No? Okay. Yeah, so this is microlocal analysis. Okay, and this is a nice book for doing illegal things in quantum field theory, okay? So if you think like, I want to multiply distributions, I want to make sense of Feynman diagrams, all these things that people tell you, no way. This is the book that helps you do that. So you have to get used to wavefront sets and things like that. But then it gives you some neat tricks to actually work these things out. So for example, there is a nice theorem there that tells me that there exists an extension of this distribution to m squared. So look in Hermander and find there exists extension. Let's call it u of xy is the extension of the Feynman propagator squared. And this is indeed a distribution where I want it. But it's not unique. Okay, but it's not unique. Life is not that simple, but is not unique. Okay. The theorem is useful enough that it also tells you exactly what the not uniqueness is. So you can actually here add some multiples of Dirac delta with some coefficients. So you can add some, you can add terms like this. A times delta of xy, where A is a complex coefficient. So let's see what we know. So I started with this Feynman diagram, right? I started with this problem which seemed a bit hopeless. Now, with the microlocal analysis, I can find out that there exists this extension. If I'm inclined towards computation, this can actually be, an extension can be computed using regularization. And then I also have a result about ambiguity. Okay, so I'm going to put this up. And this ambiguity is something really important. This corresponds to renormalization ambiguity. Because, well, if you had a QFT course before, you know that there is the renormalization group, renormalization ambiguities, counter terms, great stuff, right? So this is just a way of packaging it in a slightly more mathematical fashion. So this is, in physics nomenclature, this is called finite counter terms. So normally counter terms are subtracting the infinite part, right? But there isn't a unique choice of these, so you can add finite counter terms and still get something sensible. So these are finite counter terms. Okay, so that's a crash course in quantum field theory. Now, you can ask me, well, so what if I take a different diagram? Am I always getting this? Yes-ish, okay? So the type of distributions I'm getting here are always going to be some powers of the Feynman propagator. Yes? Sure. You wouldn't recognize it easily. No. So what it does, so it looks at something like the degree of divergence. So each graph has a degree of divergence, and then distribute. So powers of Feynman propagator are of a particular type. They have particular scaling properties that allow you to build those extensions. So you wouldn't recognize it as sort of anything related to, say, Wilsonian renormalization if you just look at Hermander. No way. I mean, I hope to be able to make some connection later, but from the outset, it's a very different mathematical toolbox. A very useful one, actually. So in general, okay, so a distribution, so distributions here are powers of GF, okay, extensions exist, and we also have another result that this ambiguity is always supported on the diagonal. So here it was just delta. in general, it's delta and its derivatives. So ambiguities are of the form. Okay, so here is, let's say, k equals 0 to n, and some derivatives of, how did they write it? Should actually write x minus y. X minus y. So, again, add indices, add signs, add different fields. You know, this is just a sort of broad sketch and skeleton of what's going on. Okay. So yeah, so then it's up to you what you're more interested in. If you're more interested in calculation, then you want to sit down and compute these distributions. If you're more interested in structural results, you say, well, all right, I know the existence, I know the non-uniqueness. So this, I think for now, this is what I wanted to say about this procedure, so that at least you know where these things are coming from. It works on curved spacetime. That actually is something maybe I should advertise more. So obviously it works on Minkowski. Renormalization tends to do that. But I didn't really say much. Maybe here, if you're writing this in this particular, at least you want to do it in a local patch, in some coordinates. But yeah, in principle, none of this is restricted to Minkowski. You can do it on general manifolds. You can, or typically you do it on globally hyperbolic, because this is the whole story. But the results of Hermander, if you read to the end, this all works on manifolds of any type. Okay, I think this is a good point to take a break. If people want to ask more questions about it, well, we can have a short question session now, and then an official question session during the break. So, any quick questions now? Okay, so then yeah, I will accidentally linger around the board. So if people have more questions, then please come down. Okay, so back to the plot. We had some nice discussion during the break, and we have those time-ordered products now that we can do something nice with. So yeah, there is, of course, a bunch of things I already told you about, so that I can use these time-ordered products to construct the S matrix. So I have the family of Tn's. Okay, so what can I do? I can construct the S matrix. Okay, so that's fine. But I also wanted this map T, this time ordering map. I will reveal the main reason in a minute. So one thing which wasn't really clear for more than we want to admit in the community is whether these guys in any way come from a binary product. So I started with a binary product, right, with this Moyal-like formula, and then I said, well, you look at these n-fold things and you extend and blah, blah, blah. Well, this is all great, but do I get a product at the end, right? This is just a family of maps. And the answer is yes, and this was actually very recent. So when I was doing my PhD, I needed that. So I was looking everywhere. I couldn't find it, so I had to prove it. So maybe somebody did that before, but this is the only reference I know. So the way I did it was actually very silly. So I'm going to define the renormalized time ordering operator. Let's do it like that. So I'm going to take all my Tn's, and I'm going to, so for let's maybe do it with argument. So for a given f which is in the space of multilocal functionals, first I'm going to factorize it into local functionals with a map which is something, and this is the silly part, this is something like the inverse of multiplication. Okay, I'm going to use this suggestive notation. Because of locality, you can actually factorize a multilocal functional up to multiplication by the complex number, so the base field. Oh, my notes are running away again. Okay, so this is something like factorizing multi-local into local. Okay, and if you want to look for the reference, there is my paper with Redenhagen and myself, and if I'm not wrong, I think it was CMP, Communications in Mathematical Physics. I think it finally appeared in 2013. So this is the reference for that construction. Now my personal motivation for that was, so I wanted a binary product that would be the product to use in the construction of the BV algebra. That was the whole point. Okay, so then this is now renormalized, right? Because I'm using renormalized TNs, this is all fine. So now again, going sort of backwards in my reasoning, I define F1 time ordered F2, and this time I'm actually using this as a definition. So T minus 1 F1, T minus 1 F2. Okay, so where does it work? So this is going to work on, for sure, on the image of T, right? So take F1, F2 in the image of T map as applied to multilocal functions. So this is the domain of, well, actually, all right. Let me be more precise. So we're going to add these formal power series in H bar. I'm still a mathematician. Take F1, F2 in this domain of time-ordered products. So I'm always going to work in this domain. So you can think of this T-map that I got via this renormalization procedure as a way to twist, to deform the pointwise product. But it turns out that equivalently, I can also think of it as the way to deform my differential. So now, another little recap from last lecture. So what we had classically, okay, so we had this space of multi-vector fields. We had, let's do free theory first. We had the free BV differential, the classical theory, and we had the product, the pointwise product, or the wedge product, if you want to be, distinguish the fact that some of these things are anti-commuting. So now I told you a way to deform it. So I'm using, actually, this is more precise than that. Just need to know which way. So let that. Okay, so I guess that should be correct. Yes. So T maps to the same space, where now I twist everything with T, okay? So that changes the product to the time-ordered product. So that's one way of doing things. Now, there's another way of doing things, which is, but why don't we deform the differential? The differential knows stuff. So here, we can also use T to deform the differential and get something like that. So quantum BV differential, which is T minus 1 composed with S0 composed with T. So let me now see if I'm doing it correctly. So I want to go back. No, so it has to be minus 1. I want to go back, apply S0, and go back. And the product remains the same. I'm presenting it to you this way because this is actually not how I thought about it originally, but this is a good way of thinking about it. You have two ways to form your BV complex, or, well, actually, there's no actual BV yet, but to deform this structure, this DG algebra, one is by deforming the product, and one is by deforming the differential. And they are related, and you can see that here, so this is deform differential, and here deform product, okay? But actually, this map T here provides a quasi-isomorphism of these chain complexes. So here, T minus 1 is quasi-iso. Okay, so somewhat in parallel, there was this approach using factorization algebras by Costello and Guillem, who were working in Euclidean signature. So it took a while since we met each other, but they were from the outset working in this picture. And I think if you're coming from homological algebra, of course you work in this picture, right? I mean, how do you deform things? Of course you deform the differential. But if you're coming from more sort of AQFT-ish perspective, then it's the product you think about. So, but it's neat that these are actually two equivalent ways of thinking about things. Now, okay, so this is a definition, right? Definition, boring. But I'm going to show you what it actually is in practice. So let's go back to this regular case where we didn't have to worry about renormalization. So, yes? Yes? Uh-huh.
That formula sounds like there is an equivalence between the two given by
Uh-huh. Yes, so that's correct.
Which is how, so the equivalence is in a bigger space. How do you
in a bigger space? What bigger space of what? Sorry.
For example, product of such a multilocal functionals going into
more general functionals. Yes. Yeah. That's right. I mean, I'm being, of course, I'm cheating a bit. So this map T leads you out of the space of multilocal functionals. So these objects here are more general. But you probably don't want to worry about it. I mean, you never have to worry about it. I mean, you just sit down and compute. But for people who worry about it, and I know that there are people in the audience who do, this would sit in the space of something called microcausal functionals. So these actually, yeah. So this is inside. Let me maybe make it a bit more precise. So this is in the space of microcausal functionals. Right, so, yeah. Functionals. So they have some wavefront set conditions on their derivatives. So their singularities are of a particularly nice type. Again, I guess for the sake of this lecture, you don't have to worry about what that is. But if you want, more detail, then I guess my paper does have that. So you can have a look and see exactly how to phrase these things. Does it make sense?
Yes, yes. And do you have a chronology here for this operator style?
Mm-hmm.
Explaining the different possible deformations that one can do.
Ah, okay. No, that's okay. So if you're thinking about something like Hochschild cohomology, or that's a nice question. Very good question. Not at the moment, but I think, yeah. So let me do a bit of advertising. I mean, Eli Hawkins, my collaborator, he has the Hochschild complex for the deformation of AQFTs in general. So maybe one can do something with that, but that's not there yet. That's work in progress. But that's a good one. Yes, it's a good question. Okay, so let me now compute this. So regular case. Okay, so say X is a regular fully vector field. So for regular things, I can use the naive formula. So S0 hat on X. Okay, I'm going to do it in a bit of physicsy notation because why not? So T minus 1, and here have S0 over d phi of X, and then, okay, so the S0 here, I'm writing it as the bracket with the quadratic part. So this S0 here is quadratic. Okay, and here, let's assume for now that we have no gauge symmetry, so S0 is just let's do the scalar field. So here S0 is free scalar field. All right, so then we have a term in the anti-bracket where we differentiate this with respect to phi, and then we differentiate X with respect to the anti-field. Okay. I forgot, there's also this T I need to apply. So what I want here is actually Tx. Okay, so now this, you remember, in the naive situation was just given like that. So now I'm applying T minus 1. There is no Leibniz rule, but there is a sort of computational method here. So there will be terms when I'm applying this whole T minus 1 to this term. T commutes with functional derivatives, so that's going to cancel this T. when I apply t minus 1 to this derivative, this is a second order differential operator. S0 was quadratic, derivative of S0 is linear. So t applied to that is just identity, because it's second order, well, it's exponential of a second order differential operator. And then there are mixed terms. So one leg of this goes to this one, and one leg goes to this one. But not so many, right? Because there will be zeroth order. There will be first order where I get the second derivative of S0, and then we're done, right? Because S0 is quadratic. Okay, so the zeroth order, that is just the original classical BV operator. And now the first order, so I have to contract with GF once, both of these terms. So second derivative of that, S0, d, okay, let's do it, x, d phi of y, contracting with Feynman, so gf of y z, and then here I have also second derivative, d squared x over d phi, so this is the anti-field, and then there is the field derivative, okay? And that's it, no higher order because this is already constant in fields. Now, a thing to notice is that if I differentiate S0 twice, then I get an operator which is the operator of the equations of motion. So now I want to use that because GF is a green function for the equations of motion. So the move I'm going to do right now is something which cannot be done if I have a boundary. So I'm not talking about BFV, because this is more tricky. Here I'm talking about the situation without boundary, where X is compactly supported, and we have no boundary. I'm free to integrate by parts. So let's start with the first term. And then in second term, this gives us P. So this is equations of motion operator. Okay. So by integrating by parts, here I'm going to get a term where I have P. This will also give me, this is local, right? So there will be a delta of xy somewhere. So gf of y z d squared x over that. Again, if you want more detail, you can look at the paper. This is a bit of algebra, really. Okay, and then now I use the fact that GF is a green function with respect to this operator. So that is going to give minus I delta y minus z. Then I integrate that out. Let's see. So, okay. So here I should also have a y because I had a Dirac delta in x and y. I integrate out this delta. So what do I get? I get x0 plus h bar d squared x over d. And now so y becomes z as well. And everything else goes. And, signs. So this is z, and this is z. Okay. Now, if you remember from Pavel's talk, this is nothing else but the BV Laplacian, divergence of this vector field X. So this is the BV Laplacian on X. This is where we rejoice, because in this naive regular case where if there was no renormalization, and if I could completely neglect it from my considerations, well, I get exactly what one expects from the BV formalism, namely that the classical BV operator is then deformed by adding the H bar term with the BV operator. Sorry, with the BV Laplacian. So this is BV Laplacian. All right, now, and you might already notice what's going to go wrong if I abandon this regular case, if I take x, which is local. When x is local, here, this derivative, differentiate once, I get a delta, differentiate twice, well, what comes out is essentially proportional to the delta, Dirac delta at 0, okay? That is not a good thing. That we cannot do that. There's been a lot of things that, we can get away with, but evaluating a distribution like at its singular point is not. So this formula doesn't actually extend to local functionals in the direct way. But after this computation, I can say, well, why don't I define the BV Laplacian through this? So now, motivated by this, define that delta is in fact, let's see, I over H bar, and then the difference between this deformed guy and undeformed. And this one is defined using the time-ordered product. Now this generalizes okay, and gives the renormalized BV Laplacian. Okay. Okay, so far so good. So this is the definition I take. So now I have BV Laplacian. You might want to see quantum master equation at some point. So we're going to have that. Yes? It is not obvious. Yeah, it is not obvious. Let's see. No, it's not. I mean, you have to. No, it's not. It's not true in general. So in general, you get something like L infinity structure. So you get like, or maybe, yeah, maybe something like BV infinity, if you want. So delta squares to 0 modulo higher orders in H bar somehow. But no, you can probably play with the renormalization freedom to get that. But on the nose, you have some more like infinity structure, which is actually very nice. So yeah, I'm going to play with these formulas a bit. So now there is a compatibility condition, it turns out, conveniently, between the S matrix and this quantum BV operator. Okay, so here, observation. So let's take this S0 and apply it to the S matrix, which equivalently we can say, well, so this is actually T composed with exponential composed with T minus 1, right? So maybe just for convenience, we are working in the image of T anyway, so I'm going to put here something which is explicitly in the image of T. So this is T applied to V. So if I use that, so this T minus 1 cancels this, and then I will have S0 composed with T, and then I will have the ordinary exponential, IV over H bar. Now using the definition of, where is that? I don't have it anymore. But using the definition of S0 hat, S0 hat was T minus 1, 0, T. Can write it also with S0 hat. So it's T times S0 hat E2 IV over H bar. So this is just rewriting things. But now, again, if I'm working in this regular case, I can use the formula I have just computed. Okay, so here I find that this is T composed with, okay, so we have, actually T applied to, so we'll have the exponential itself, and what else? Well, there will be S0 acting here, it's a derivation, S0V, and there will be delta acting there. So I'm just going to give you the result for a sec and then justify it. Signs, okay. Never get away with this. Okay, so so this is second order term where I differentiate twice with the BV Laplacian and get something like that. 1/2. And there's going to be a term of this form, IH bar, delta V. With any luck, minus, I might be able to pull this off. Let's see. Sorry. Minus IH bar. Okay, let's see. The signs are probably wrong. Sorry about that. But the rest of the equation should be fine. So, yeah, let's see. 1I here. Okay, so this would be plus. This is minus. No, that actually might be correct, or I made the even number of sign mistakes. So what comes out of there is T over H bar times, I'm going to combine S0 V. I'm going to write this as the bracket. Okay, so S0V plus 1/2 VV. I'm pulling out one factor of IH bar in front of everything. So IH bar. So that clears this. One of those. These guys come with the plus, so that's okay. And this guy comes with the minus. Incredible. All right. not done yet. So here I can pull these together. S0 plus V, 1/2. And I have to correct for what I added. So minus this. And similar here, I want to write something which has S0 plus V, okay, which has full action. So I'm going to do this, V plus S0, and correct for what I added. So plus IH bar delta S0, okay? And now I can group it into two terms. So this is 1/2. So this is the whole S. So S with itself minus IH bar delta of S. Okay? Minus, and then same equation with S0. S0, okay, also this way, delta S0. Okay, so what do we have here? This guy is the quantum master equation for the free theory. So, quantum master equation for the free theory. Okay, and here it's quantum master equation for the interacting full theory. So QME for the interacting theory. Okay? So, in a sense, this is somewhat compatible with the idea of doing perturbation. So I start, if I have a theory that satisfies quantum master equation, I start with S0 that satisfies that. Then, if there is equivalence here, right? So if I find S theory such that the interacting quantum master equation is satisfied, then going back to this board, the S matrix is invariant under this either classical BV operator, or you can say that this just the exponential of V is invariant under quantum BV operator. So in a sense, okay, you can now think about the quantum master equation as invariance of the S matrix under the BV operator of the free theory. So this is S0, right? But what's actually interesting here is that, well, we are working in this perturbative sense, right? So we fix S0, we build the time-ordered product, star product, everything for the free theory, right? But this invariance of the S matrix actually spits out a condition that can be formulated in terms of the full S. If I was clever enough to choose my free theory to satisfy the quantum master equation. So that's an observation. Now, I'm going to show you why this is a useful observation. So, any questions to this? Sorry? Yeah. I mean, in the absence of, for the free scalar field is obvious because both terms are 0, right? Huh? The what? 0 is not, but right, but on the other hand, S0 for scalar field doesn't depend on anti-fields. So then both terms, yeah. So it doesn't matter how you renormalize things. It has to be 0 anyway, right? So for the free scalar field is obvious. For say electromagnetism, you might want to do some work, but not too much work. But yeah, it's kind of it's a natural thing actually to start with the theory that satisfies the QME. Okay, so now I want to say something about the interacting BV operator. So we're working here with S0. That's obviously not all we want from life. So how do I introduce interaction? Again, back to the last lecture, I stated it very quickly, so I don't expect that people remember. But so let's recall. In order to pass between free and interacting, I gave you something called the Bogoliubov map. So RV of f, which was defined as time-ordered exponential v minus 1 star v f. Okay, minus 1 was the star minus 1. So this was the Bogoliubov map, and it takes, let me just think about one thing. Okay, let's do it this way. Okay, so let's have t's explicitly in this formula. It's slightly a matter of convention how you want to organize this, but I want to make my life easier and yours as well for what comes next. Okay. So F is a classical observable. And here there is the time-ordered product. Okay, so how do you want to think about it? So F is classical observable. If you are somewhat familiar with the idea of deformation quantizations and things like that, T can be thought of as quantization map. So that gives you something which, morally speaking, lives in free quantum theory. And then the rest of this stuff is there to give you something which lives in the interacting quantum theory. So this whole thing is interacting quantum observable. Okay. Some intuition behind it. If you have done a QFT course, there is something like the Dyson series formula for interacting observables, maybe, right? It's something like this. So one way to understand this, okay, I can evaluate it at 0. So this is evaluation at phi equals 0. And here is a heuristic argument. So in nice situations like Minkowski vacuum, the evaluation at 0 will factorize somehow. So this would be, you could put that on top and divide it by that. And you might recall from the previous lecture that the T map is actually, morally speaking, the path integration. So what is this? This would be the path integration of I over H bar V times F. And here I'm integrating with a Gaussian measure given by S0. It doesn't make sense, so whatever. But I guess in Euclidean, you could probably make more sense out of it, and definitely in finite dimensions. So finite dimensions, this is all fine. Gaussian measure. To keep my maths credentials, I'm going to give it quotation marks. And what? So now this term, right? So this is divided by this. Well, look at that, right? It looks, something probably familiar, or maybe familiar if you have ever seen sort of traditional QFT textbooks, a formula for the interacting observables, right? This is the sort of normalization by just integrating the measure. Cool, so that's where it comes from. This is the formula of Bogolyubov, and I'm going to use it to further deform my S0. So now I want to get the interacting BV differential. So I'm going to use RV for a good cause. So interacting BV differential. So that is RV minus 1. Again, this is a definition, actually. So S hat V, interaction V, composed with S0, composed with RV. Okay? That's the definition. Now the computation. And observation maybe before that. So note, by the way, that S0 is actually a derivation with respect to star. I didn't tell you that. I should have told you that. But this is a nice exercise for the audience. Check that S0 is a derivation with respect to star. And the computation is very similar to the computation I did when I computed S hat. So you can probably do it at home. So S0 is a derivation with respect to star. Okay, so let's compute of F. Okay, I'm going to keep that guy. And now S0 attacks this whole ugly thing. I said derivation, right? So I'm going to let it act on this, Leibniz rule, times that, and then the other way. So, okay, so S0 on that, TV, star, and just repeat the other term. It's going to be 0, so don't worry. And the other one, again, well, I guess it's reasonable to assume that V is even, because then we would be in trouble. So we can forget the signs. So this is a plus, and then we have ET, IH bar, sorry, that was minus 1 here. Okay, and here we have V, again, minus 1, star, and now S0 acts on this part, right? S0, V time ordered F. All right, so now using the fact that S0 is a derivation, we split it into these two terms. Similarly, you can write S0 acting on the inverse of the S matrix as, well, it's proportional to S0 acting on the S matrix itself. Again, there's nice algebraic way of writing a derivation acting on the inverse. So this term, this is going to vanish as long as the quantum master equation holds for both S and S0. So this is 0, assuming QME for S0 and S. This is a G. Okay, so this guy is out, so we are only dealing with this. And here I'm going to write it as follows. So this is d over dt. I'm going to write it as a derivative of an exponential. So I over h bar t v plus tf, okay? It's proportional, right? There are some I over h bars. But you can write this again as an exponential and use the formula I already gave you. Okay, so you don't have to do this computation again. I don't have to do this computation again, and everybody wants a coffee. So I'm just going to refer to the computation I already did. So this is going to give us, the first term is gone, so we have RV minus 1, and here TV minus 1 star. Again, I'm not going to go through the full gory detail of this, but if you're interested, you can fill it out based on my previous computation. So we will have a bunch of terms that that can again be gathered into this QME for S and QME for S0, and some terms which involve F. So this is assuming, again, assuming QME for S and S0. Okay, I'm probably good. So there will be piece with S0, which comes from just applying that. And there's going to be, again, a piece from the BV Laplacian, which will actually give us that. And that. Great. Now what do I notice? I notice that this expression here, that can again gather it into RV. So this gives me RV, cancels RV minus 1. Magic. I have now the formula. Which way am I doing this? Okay, well, it probably doesn't matter, modulo signs. Minus IH bar delta. Oops, not V. Sorry. I want a coffee. That's why. That's why I want a coffee. Okay, no, there's only terms linear in F survive that procedure. Which again, look at that. So this is the full interacting BV operator, classical, acting on F minus delta of F. So this way I can actually also reproduce the interacting quantum BV operator. And again, I did the computation for non-renormalized case, but now I can use this definition again for the renormalized case. Use this definition to generalize to the renormalized case. Okay. How are we with time?
25 minutes late, we had
5 minutes. Okay, that's great. Yeah, so that finishes sort of the computational part of thing. But there's a funny question here. So if you look at this formula again, what happened, right? So RV is something extremely non-local, okay? There are these time-ordered products, star products. There's no reason why anything there should be local. But then, assuming this quantum master equation, right, and doing this computation, I found out that no, actually, you know what? This operator I defined at the beginning is automatically local. So this is, now the question I can ask is this a coincidence of the fact that I forgot renormalization, okay? This whole thing was done neglecting renormalization. So if I renormalize, right, do I have any reason to expect that this is going to be local? No, maybe. So there is a result which, well, somehow was derived for an entirely different reason, which tells me exactly what I need, that what comes out there is local. And this is called anomalous master word identity. So I'm going to state it on the end. So anomalous master word identity. So this was due to Brennecke, Dutch, and later generalized by Holland. Okay. And this says the following. I'm going to write it in my notation. This is not how the original papers write it. But okay, so again, I'm going to state it for the scalar field for now. For now. Tomorrow, the gauge theory. If you don't come, then you miss out all the good stuff. For the scalar field, so this tells us, okay, no, you know what, I'm just going to do it even nicer. So because we have all this BV machinery, so it tells us what happens if I apply this classical BV operator to the time-ordered product of the, to the S matrix of something, okay? And note that here the product between these two things is just the ordinary product. So this is, in other words, ds0 over d phi contracted with d over d phi dagger of this. But the product here is the pointwise product, not the time ordered. I'm emphasizing it because it actually makes a huge difference. Okay, so they say that this is equal to that, time ordered. And now, this is a gift from heavens. This is exactly what comes out from the naive computation. So, oops, S0 plus V, S0 plus V. So we are getting here, oh yeah, sorry, no, let me maybe write this step by step. So what they state is just that part of things. Okay, so kind of comes from this bracket plus, let's maybe write it down already like that, something which they called anomaly, which depends on V. Okay. And they prove that the result is that this anomaly here is local. So this is anomaly, and this is local. Yay! So you know what that is? This anomaly term is exactly the renormalized BV operator. It plays the same role if you do this whole, careful renormalization procedure a la Epstein-Glaser. He can definitely explain to you how to do it. He has a beautiful, beautiful book which has all the computations, so a bit of advertising. Read Michel's book. This identity is there, and everything is worked out very nicely. And the main result is that this is local. And therefore, if I do the renormalized version of everything here, I can just replace this delta with the renormalized VV operator coming from the anomaly. Okay, I think this is the nice moment to finish, and tomorrow I will do the same for gauge theories and talk about some non-perturbative perspectives and renormalization group. So, thank you for your attention. I think it answers your question about anomalies.
Of the Laplacian BV operator, okay? Thinking to the finite dimensional example, the Laplacian BV operator is related to choice of integrals, sub-Berezinian.
Yes, that's right.
So my question is there here some state hidden in so what's the analog here of this?
Yeah. So the state is evaluation at 0. So it's an algebraic state. So state understood as a positive normalized functional on my algebra. So taking the time-ordered product and evaluating in this state is the same as taking path integral, morally, right? So then the change in time-ordered product is the change of how you regularized and renormalized your path integral. So somehow, if you want this intuition, so commuting things with t means that you want to pull them under the integral sign, right? So there was this move where I had the classical BV operator acting on t of something, and then I swapped, so I had t acting on the quantum BV operator. And this is because you can imagine this under the integral sign where things have to be 0 modulo total divergence, and delta is the total divergence. So that's the geometrical intuition behind it.
Short question, please.
So usually, like the anomalies and in the word identity, this describes some like classical symmetries which are not symmetries of the quantum theory.
That's right.
So my question is like, what are the symmetries here in that example?
Okay. So I haven't talked about gauge theories yet. So, but then you can replace this. Say, so instead of free scalar field, you can do electrodynamics. Okay. So this would be the Lagrangian of electromagnetism, free electromagnetism, or linearized Young-Mills. And then from that, you can compute, so take an observable, right? And then this difference between how the renormalized BV operator acts and the classical BV operator acts is the difference between classical and quantum symmetry. So let's say you have something which is invariant under the classical symmetry, right? But the anomaly doesn't vanish, so delta doesn't vanish. So that thing wouldn't be invariant under the quantized symmetry, morally speaking, yes.
And here for the scalar field example, should I think of like a global symmetry or?
Well, you can think about it actually, so because S0 has, so here the VV operator knows about the equations of motion. So this tells you something like, it's like Schwinger-Dyson equation, so it tells you how classical equations of motion are violated in the quantum case. So it measures the difference between that.
Very short, please.
So you said in general, okay, this renormalized BV operator does not square to 0.
Yes.
And you think that maybe by renormalization it should be possible, but I don't know, is that always possible, or I mean, that's also supposed to be some sort of anomaly,
It's not
right?
always possible. I mean,
Okay,
in general, you have some sort of infinity structure. Like what comes out of the box is, yeah. It actually, maybe for Alberto, I can write something very quickly. So there is something like this. So if you have, or actually maybe better that. Yeah. So this property.
Is still satisfied.
Yeah. So this is then modulo the bracket.
Yes.
But there are plus higher brackets.
Also there, okay.
Okay, and these higher brackets form an L infinity structure. Okay. So this guy together with the whole family of higher brackets is an L infinity algebra. So that's what you have.
So delta is a derivation for the
yes.
whole L infinity algebra.
Right, yeah,
okay.
yeah. Mm-hmm.
Okay.
Okay.
So these are automatical.
Sorry?
This is automatical.
This you have to prove, but it has been proven.
Okay.
Yeah, this comes again from the renormalization story,
okay.
that you can do that. Mm-hmm.
Okay, so thank you again.
Thank you.
Time for